Sorry to those of you out there that it took a minute for me. Good job. Okay, share screen, share sound, share. Great. Okay, let's hear these. Sam, want to share anything? Cool. Yeah, okay. We can talk more about that. I have put one. Well, I emailed it out, but I may not have put it up here. I can add that really quick here. Well, I'm thinking of it. Come on, Moodle. Well, no comment. Okay, that's up there now on Moodle. Thanks for sharing screen. Good. Okay, and are we rebooted? Yeah, let's see here. That's 3. So, were you here last week, Sam? You were, weren't you? Yeah, and since that, since I've just still kind of felt like, what the hell is going on? Well, we'll revisit that bit today, then. Any specific questions about where you think you might be having some faltering on that? Yeah. Cool. Okay. Okay. We'll look at tasks again today. We can talk about that for sure. Fletcher, anything to add out from the ether?
Yeah. Yeah. Hello. Can you hear me?
Yep.
Yeah. Not really. Just kind
Great.
of diddled around, playing
So
it right.
Yeah, it looks good. So we're defining a SimStep here with an envelope, and then every second, every 2 seconds. We of course play these together. Cool. Thank you. Nice job using fork there. Anything to add, bro? Okay, so this is just playing around. Finding a synth. Yes, here. Cool. All right, wonderful, thank you. Matthew.
Mine's on the bottom, sorry. I just take one minute. Yeah, I guess this is kind of the first week where there's been a lot, actually a good amount of things I'm quite certain about. So
Yeah.
I've got a few questions for later down the road. I tried to go through that documentation, but as you probably know, some of the documentation is incredibly dense.
Yeah.
And so it's like trying to decipher things. So I guess what I tried to do is I really wanted to make things a little star with the products. I'm like, well, that'd be cool if I could program that.
Yeah.
My problem is, you can see in 110, I tried to assign the rhythms, but I don't know how to get it to run through that from top to bottom. So the only way I can get it to work in 114 at delta.rate is if I had it do the dot choose at the end. I tried like a million different extensions of it. I don't know what I used to get it to run through that rhythm array.
Yeah.
Or
Yeah.
if you can do it, that's pretty cool.
So there's a couple of ways we could have handled this.
And that's what I was trying at first, because I knew that worked for the frequency array. So
So we would call the same array, and then here, no, we would actually mod afterwards.
I guess we'll get to this later. If you scroll up to the very top of the page, I guess just my biggest question is I'm not quite wrapping my head around how line 11 gets it to run through things, what dot mod dot. And like I said, I'm
yeah.
trying to get to that.
Does it, what is, oh. Okay.
And so the idea of index number increasing one makes sense to me, but I
Yeah.
just don't know how to.
So modulo, modulo is the remainder of long division. So if we have 5 divided by 2, how many times does 2 go into 5? With a remainder of 1. So 2 mod 5 equal to 1. Where did we go? Here. Oh. New. Supervisor, catch up. New. So if we go, we got. Oh yeah, hold on here. So 2 mod 5 gets us a remainder of 1, right? Likewise, because if we divide, cancel. Hold on here. Hold on here. Yeah, open up whiteboard. So. Over here. 5. Oh, 5. Over here, 5. 1, 2. So how many times is 5 going to 2? With a remainder of 5. What is that actually though? It's no. It's always about the based on the remainder. What am I missing? Sorry, I'm not quite waking up yet. Let's start over.
This creates my question, very questionable.
Yeah. Okay, so let me start over. So oftentimes, first off, modulo is oftentimes written with the percent sign, which is weird in itself, but just so that if you see that in other coding environments, that's something to be aware of. So again, modulo is the remainder of division. So if we have 0 divided by 2, 0 goes into 2. Oh man, sorry. You want to teach this section? For some reason, my brain is not working this morning, Maya. Hold on here. Let's just, come on, Michael, music. Wake up. So I think we can actually go, can we do this, that mod? So let's know if we got 0.mod. Okay, so does this make sense? If we have, oh, I need to remember to fix that. If we have 0.mod 2, this gives us 0 because 0 goes into 2 0 times with a remainder of 0. If we have 1 mod 2, we have 1. 2 divided by 1 is equal to 1. Oh, is equal to 2. Oh, sorry. It's 2 into 1. Excuse me. Which gives us 2 goes into 1 0 times with the remainder of 1, essentially. Wait a second. Why am I? Hold on a second here. I apologize. This dot notation is messing me up here, and I apologize about this. We'll come back to this next week. I don't feel like wasting time on this right now.
That's okay.
Yeah.
As well, but what is, I guess, larger? How does it work?
Where? In line 11?
Yeah, what is line?
It's essentially saying when index value gets to the size of the frequency, once we go to, so yeah, because so we're posting here IDX before our mod and afterwards, and we really should be posting. Let's do one more time here. IDX.post. So initially, IDX is set to 0. So then we add 1, and so IDX gets set to 1. Freak size is 1, 2, 3, 4, 5, 6, 7, 8. So 1 mod 8 gives us back 1. It goes in 0 times with the remainder of 1. So then next loop, IDX is still set to 1. We add 1 to get 2. 2 divided by 8 is 0 with a remainder of 2. So it stays 2. Again, we add 1 becomes 3. 3 divided by 8 is a remainder of 3. 4 divided by 8 is a remainder of 4, etc. Until we get to this last iteration here, 780. Yeah.
Why is it, why is it say one and two,
8. It's always 8. We're not posting free size. So
oh, so this is a fancy workaround using what we know about math.
Mhm. because if we have 8 divided by 8, 8 goes into 8 one time with a remainder of 0. So we take that remainder and reassign it to IDX
So that,
and get 0.
that's just kind of like a jerry rig workaround to get it to go back to 0.
That's not jerry rig. This is used really quite often in
Sure.
working with arrays. Yeah.
That's actually super cool. And since we know that Superfighter works top to bottom, just throw that in. Okay, I got you.
Yeah. Yep. Cool. Okay. Let's see it here.
So, again, why is it
Say again.
why not set it to 0 whatever it is? It's always going to be the same value. It's always going to be 0. Why not set it-
It's not. We're taking the remainder, not the product. So 2 mod 8, 8 divided by 2, or rather 2 divided by 8, 2 goes in 0 times. 8 goes in 0 times, rather, with a remainder of 2. So we're taking that remainder piece. Maya, anything to add? Cool. Very cool. Nice gesture and statement there, Maya. Thank you for that. I like the patience that you took with it. It has a really nice sense of space. I'd like to see it on both speakers, just from a standpoint of why not. But that's a really nice piece. Thank you. Danny. Say again. Great. Cool. Cool. I love the buildup. Feels great. Okay, I wanted to look at this really quick, Cole's piece. So just really quick to recap on SIMPDEF. So what is a SIMP definition? Mm-hmm. And what are those rules? Well, what's one of the most important things we get from a SIMPDEF? It's like a class. That's exactly it, Sam. It is a class. So if we're thinking in object-oriented programming terms, it's like a class. And what happens is when we compile this SIMPDEF, the program, oh, I forgot that's gonna try and do that again. The program creates something called a synth graph. So in this one, let's keep this here. So we're defining we're defining a series of arguments. And what are these, what are arguments? What is the relationship of arguments to an eventual sync? The arguments defined, there are things we can change on instantiation or set later on after we've instantiated. So Cole here shows us this example where he's putting in a new frequency instead of the one that he initially set. Likewise, he's able to change C ratio. Oh, nice, carrier ratio. It's changed when he instantiates a new synth. Yeah, so these values here are the default values. If we called this with no that's the default that's set up. So it can be played without passing in any argument values. And whatever the defaults are that were provided at the time of compiling is what will get played. Baseline stuff. And so here, he's passing in a different frequency. 62 converted to cycles per second is equal to 293 hertz, roughly. Huh? Yeah, because 60 is C. Okay, so these are things we can change in real time. The next piece that we have here are variables. And what are variables and how do they differ from arguments? Yeah, so what can we assign to variables? Pretty much anything. We can assign signals. We can assign envelopes or other pieces of data structure. So, and data is the big one. So we can also assign integers, floats, strings, etc. Yeah. So global variables, again, we don't call them technically global variables, but there are a number of global variables. A through Z, lowercase, serve as, they're called environment variables. So A can be equal to 20, and then we can call A back. We can also create longer, more explicit environment variables using the tilde notation. We can override it, of course. And those then are accessible within synth blocks as well as outside it. So if we're looking though back at the synth that Cole defined here, in line 8, he's doing two things at once, which is totally fine. He's defining an envelope. Oops. It's right here. And then he's passing that envelope to an envelope generator, which creates a signal which gets stored in the variable on. Just for a moment, let's do new page. we can take this here. These default values are set to 0.01 and 3. Remember, we can go test.plot. And this is the envelope that Cole has created. But again, Cole is taking this envelope, and instead of one of the things he could have done instead on you could have defined another variable on shape. And it's still going to compile because now he's defining this envelope shape, assigning it to the variable on shape, and then passing it in as the envelope shape for this, what will become a signal. And this is the hard part, this movement between data structures to signals over time in SuperPython. It's very confusing. Any questions on lines 8 and 9? This is not a signal. What is a signal? Yeah, but what is that? Sure, what else is it? Yeah, what kind of information? Data, yeah. And how is it different than static data? It's happening over time, so it's always ongoing. So a signal, not recurring per se, but like we could have the number 1 as a signal. It just means that we're passing 1 constantly. And that's a signal. It's happening over time. Essentially meaning there's no end to it until we kill the entire sim. Once it's going, there's constant data being created and moved through the signal chain. In this case. Whereas on gen is essentially just a shape or a packet of data. And it defines a specific set of data over a bound range. In this case, I think it's like over the course of 2 seconds. So we pass, oh, excuse me, I'm so sorry. To eraser. On, excuse me. Dot perk. We pass this shape to the UGen on gen, and it creates that continuous signal over time. The major difference here, remember with onGen, there's this done action. There's also this ability to use a gate to re-trigger an envelope. So we could actually have this envelope being played multiple times in time. So let's say we'll take this line here. We're going to comment it out. We're going to go 0. Gate, we're going to do dust.care, which creates another signal. I'm going to say 2. So whenever dust goes from 0 to 1 randomly, approximately 2 times a second, it triggers this envelope generator to reuse this shape. Again, it's just a signal over time without any technical end. What What is what? Perk is just a type of shape. So it's defining a percussion type of shape. Yeah, so on perk looks something like this. The other types of methods we can use for envelope are things like sine, which has a smooth attack, doesn't have that same type of hard attack. ASR. Let's find a different one. It's not showing us that sustained because the gate isn't part of the test here. But essentially, these are each different shapes of an envelope. Why might we want to use different envelope shapes? Yeah, because it changes the quality of the sound if we're applying it to an amplitude particular. Okay, cool. All right, moving back here. So we're creating an envelope shape. We're creating a signal that's defined by that envelope shape and storing it in the variable on. Then we're doing some modulation, frequency modulation based synthesis. Cool. And we're multiplying that. Let's actually be explicit here. We'll go. We're going to make one more variable called sig. And instead of car, we're going to use sig. So we've got our modulation thing. We're going to ignore that for the time being because that gets into synthesis theory and not as much to do what we're talking about here. But essentially, in line 12, we're creating an audible range frequency or signal. In line 13, what are we doing? And what else? So what does that get us? Gets us an envelope, kind of.
Well, it changes the signal over time.
Yeah. So if we commented out this line, we just get this signal. When we multiply it by this envelope over time and the relative amplitudes, we get shape and we get a peak volume essentially. The amplitude is not changing over time in this instance, no. So, cool. Now, let's say we wanted to actually change these things in time. We might have something like let me think here, what I want to go. Yeah. And then, Again? Yeah. It tells it then to have a float. We'll talk about that in just a second here. So right now, we've created a task, and this was the part that got a little confusing last week, and I apologize. And a task just says we're going to do whatever is contained within me until there's no more instructions. In this case, we're saying we're going to create an infinite number of things to do. So there will never not be instructions.
Envelope is, and so I bring the envelope one moment and find a third one. Is a when you're multiplying
Let's,
my brain said, okay, figure what the number is by the number the next number. All of a sudden you get the value, but that's not true. Because the end is actually a the generator,
yeah,
which is determined something in the number, decimal,
yeah.
and then the most time together with the signal will be normally multiplied. A signal, and then normally multiply a signal times the envelope times the answer.
Yeah.
To get a signal out of the field.
So let's say here, let's say this. Let's say we've got a signal. And let's say this happens over the course of 10 seconds. Okay. Let's say we've got another signal, so we're going to call this one sig, or whatever. We call it actually sine. Okay. This is just a sine wave. Everyone sees that? So then let's say we've got another signal over 10 seconds as well. We're going to call this one on. So this signal, this top one, goes from 1, 0, -1. This one goes from 1 to 0. Okay, we're going to have one more signal. We're going to call amp. And it's at 0.5. Yeah. Tell me.
When you say it, that's a line. I mean, that's it's a graph. You have an X and a Y. You have to have two numbers, common numbers, and then multiplying numbers on my brain can compute the really detailed stuff. So I don't understand how you're taking the essentially a graph, finding a point, determining a single number, you can then multiply times something else.
We're going to get there. So let's say we're going to take this moment in time right here. Is that blue coming up okay?
Yes.
Okay. So let's assume or rather, can we all agree that at this moment, we've got 0, a value of 0 for our first signal, We have a value of 1 for our second signal. And we have a value of 0.5 for our third signal. Is that okay for everyone? So at t equals 0, so time equals 0, the beginning of time, we're going to multiply 0 by 1 by 0.5. What does that get us? 0. Okay, cool. Is everyone okay with that math? So just, that's one sample in time of our resulting signal.
Where are you getting the form on that? What point on the time was it looking at?
We're looking at time 0. So we're just going straight up and down. We're saying these are all signals, but all we can do is look at an instantaneous moment in time. So at time 0, the sine wave is at 0. It's right there at our cross point. At time 0, our envelope, which is just a line going from 1 to 0, is at 1. At time 0, our straight value amplitude is at 0.5. Three different signals that we're multiplying together. This is how we get to this idea of how do we multiply signals together. You got to go time moment by moment. So we have then essentially 0.0. Great. Okay, let's move on to our next point. We'll go right here next to it. Is that green coming up at all? Yeah, no. Okay, so let's say here at this point, and at this point, let's say we have some values of 0. Oh, let's make some easy math. Let's assume 0.6. Okay. We'll assume 0.6. We'll assume 0.8, and we'll assume 0.5. So we're going to multiply those three together, 0.6 times 0.8 times 0.5. That gets us 0.24. At time, let's say time equals 1. We've now got 0.24. So we're going to take at that time, we're going to then create a little dot at 0.24. Yeah, is that okay? Yeah.
Why, if I'm looking at that top graph, it's going to be 0.6, it's going to be 0.6, 0.5. I'm guessing.
It's going to be 0.6 and then whatever t is, our time, number of samples that have elapsed. In this case, we're saying t is equal to 1. Here's the takeaway. The resulting shape is going to be a multiplication of each of these over time. So essentially, we've got a envelope that is transposed on top of that sine. And then we've got a factor of 0.5 that's cutting the whole thing down. So all we can do is we can only multiply moment by moment. And that's how we figure out the resulting wave or signal. What happens if you transpose this linear line on top of the sine wave? If you multiply the two together, eventually when you get to 0, you've multiplied down your sine wave. And again, that follows the shape of that envelope we're talking about. right? We're going from 1 to 0 over time. If we multiply a sine wave 1 to 0 over time, eventually it equals 0. It's no different than if we do it in the hardware domain. So let's say we go brute force here. I grab the gain knob on my audio interface. It's equal to 1 right now. Over the course of 5 seconds, by the time I get to 0, we're multiplying by 0, and so we don't hear anything. I just multiplied moment by moment the value of the knob by the signal to get the resulting signal. Does that make sense, Bearcat? Say again? Yeah, so all we're saying here is for each sample, multiply the 3 signals together and give me the resulting value. And then we pass that on to the audio interface output or wherever we're going with that signal. In this case, we pass it on to KN2, which creates 2 signals out of it, and then we pass it on out to our hardware outputs. Does that make sense for everybody? Anybody does that not make sense for? This is important. Yeah. Yeah. Mm-hmm. Yeah. And again, this is where this idea of a synth graph, which is probably rather abstract at the moment. So all we're doing when we're saying, let's create a synth graph is we're working down this whole synth definition. And we're saying, okay, we're going to create a signal that's a line. And it's going to go from 1 to 0 in 10 seconds. So we create our line. In the next line, we create a sine oscillator. And then we create another sine oscillator. And we say the 2 of these are multiplied together, giving us another signal. So at this point, by the time we've gotten to the end of line 13, we essentially have 4 signals. This one, which is line, a sine os here, or 3 signals, where the first sine os is affecting the result of the second sine os. And in line 14, we multiply them together to get our output. So a synth graph is doing just that. It's essentially creating what is the signal flow internally of this resulting synth. And the piece we're ignoring in line 14 is that we also have this value 0.5 or whatever it is that also gets multiplied together and gives us that resulting signal. And in SuperCollider, it just looks at those values moment by moment to figure out what they would be. It doesn't matter. Here becomes mathematical, precedence, whatever. So if math precedence matters, you want to be careful about it. Otherwise, I like to think about it in terms of human readability. For me, I think it's easier to say, okay, I've got a signal, I'm multiplying it by an envelope, and then I'm multiplying that all by a constant value, but it's not going to make any difference. And what we're trying to do right here, also Bearcat, I didn't say this before. This pole, right now we're pulling our line so we can see that value over time. And let's actually do this show scope. Right, so we can track as this starts at 1, we see full value over here in our stethoscope. As it goes down, we're multiplying this ongoing sine oscillator by this value until we get to 0, in which case that results in nothing. And as Charlie points out, because we can follow mathematical sign precedence, with multiplication, it doesn't matter. Precedence doesn't matter which order they come in. Yeah, so let's say we've got an sine amp on, something like that, right? And what we're going to do is here, just to really thoroughly confuse everyone, we're going to say sine amp on going to be equal to just another sine oscillator. So it's going to be in the KR because we don't care. And it's going to be super low frequency. I will say twice per second. And I'm going to range it up to 0 to 1. So we're no longer going -1 to 1, we're going 0 to 1. And then just to really fuck with everything, we're going to multiply this resulting signal as well by sine amp on. And so now if we went back to our whiteboard, we would actually be adding in a whole nother signal that we're multiplying in moment by moment with this, making that pulse. And again, we're just applying it to the amplitude domain. We could apply it to frequency, we could apply it to phase, we can apply it wherever we want. That's where we start getting to synthesis theory. That's what we're doing. We're applying an envelope to amplitude. Yeah. Yeah. So where would it matter? The only time it would matter is if some sort of mathematical order of precedence would cause an issue. So if we do addition or subtraction, where those get placed in the algorithm matter. If I'm taking amp and I go amp plus, well, let's see here, 1 plus amp, something like that. This is still going to compile. But if we wanted to apply it specifically here first, before we're multiplying it, that's a bad example, but right, that's where mathematical order of operation matters. And again, these synth graphs are setting up a system where it's looking at it sample by sample. Okay, I think this has actually been great that we've gone very slow through this. Sam, are you feeling any better? Or are you just totally frustrated with me? A little of both? It's okay. People can be frustrated with me. I got no ego about it. Do you have any questions that we want to answer? Do you want to set up some time with me sometime? That's fine. Why don't you think about things, set up some time with me next week. I know you're feeling a little overwhelmed. I want to just give you a chance. Bearcat, how are you feeling with some of this signal-based
I don't,
synth graph stuff?
for the most part, I don't have a problem with code. What I have a problem with, my basic math has always been, always will be. And so I sit there and have to call it, well, wait, if you're going to point out a line, we have to have two numbers. That doesn't happen. So everything I've known in chaos,
Mhm.
my brain just gets stuck.
Again, just to say, we do have two numbers. These vertical arrangements are the second number, tying everything together. So here, our numbers are 0, 0, 0, comma 0. We're not ignoring it. That's where right here, t equals 0. We're just not calling it y. We're calling it what it is, time.
If the sign of the envelope and amp are all signals, but all signals have an envelope made up of an amp, of an amplitude, and a time, and a,
Mhm.
it's a few places, wrapping itself inside itself, and then inside itself, and then inside itself. So I'm wondering how these get separated into three different things when they are things, and are components of each other, right?
Well, they're only components of each other because we told them to be in line 17.
And then a sine wave has an envelope made up of a sine, amplitude, and
Yeah, and what's the default envelope then of a sine wave? Let's say we've got a sine wave here. Oh, that's so off screen, and I apologize about that, but what would the envelope look like? The envelope would just be a single block of 1, whatever the max amplitude is.
so the envelope of the sine wave is. I don't want to spend anything.
Cool.
Here's the envelope of the sine wave. No, the envelope of the sine wave is not the average. It is the number, it is these numbers, that is in the top. No, it's not, it's the entire wave.
What is an envelope?
It's a sort of base that determines, I mean, you can use it to determine a lot of things typically, or most of the time. We use it to determine the amplitude of the time.
Okay. What else? What else is an envelope? Something that contains something else. That's a synth def for a class. An envelope contains something else. Say again. I don't know if these models are helping you, Cole. I know. I was hoping there was a recording. Oh, there is. Okay. Let's look at some different code. I think this will open. We'll see. Yeah. 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 That's it. That's it. Let me see if I can't fix this up here. Oh, there's some issues. Okay, never mind. Well, I want to play you guys a piece. This is actually an interesting moment. So, let me see if there's another. No, that's cool. Yeah. Really simple piece that gives a great sense of how we can use envelopes. It may or may not make things simpler. I don't know yet. Okay. Okay, are you gonna work? No. Let's see Windows, not fine. Bummer. Get away with it, huh? Static text. Okay, well. Well, that won't work, but that's okay. So. Here's a piece. And for those of you who don't mind looking at scores, here's the original. Here's a score. Okay. And what happens is what used to happen in this, but SuperClever has changed the way it deals with creating windows. What used to happen is that a window would pop up that just had elapsed time and essentially would go from 0 to 9 minutes, and it would show you the time of how long this program had elapsed. Okay. So just imagine that there's a window that pops up of 0 to 9 minutes. What's happening in line 41 here? What are we doing? We're defining an envelope. In this envelope, looks like that. Okay. What are we doing in line 46? Defining another envelope that looks like this. And then in line 51, doing another envelope. Okay. So we've defined 3 envelopes. Everyone okay with that at this point? Matthew, do you have a question? Oh, sorry, I thought I heard you. No. An envelope can be anything. It can be anything. It's just data over time. When we were using it before with Cole's example, we were just defining a note or a single shape. It went up, it came down. What do these envelopes look like to you? Do they look like something we might use to define a note? One of them does. The bottom one kind of does. It goes up real quick, stays at 1, and then comes down over a slow amount of time. Huh? They could. They could. Here's the other thing to notice, though. How much time is being taken up by these envelopes? .400 seconds. So an envelope is just a container. It's not a single note. It could be amplitude, it could be frequency. It's just signal. It's just data over time. So in this case, over the course of 400 seconds, we go from a value of 6, and then over 35 seconds, and again, remember this third, okay, so we've got 3 arrays here. First one is values. Second one is time between values. And the third one is the curve shape between those value points. So we define 2 values, 6 and 0.7. We got 6, 0.7. It happens over the course of 35 seconds. And it's got a shape of negative 3.9, huh? 0.07. Thank you. So nearly zero. And this last number again defines the shape of it. We then go over the course of 135 seconds from 0.07 to 0.09. Everyone okay with that? Why not? Line 42 is just defining a series of values. Line 43 is defining the time it takes to go from value 1 to value 2, value 2 to value 3, and so forth.
Zero
50 seconds. Yep, and that's this chunk. And then 80 seconds to go from here to here. And then 130 seconds to go from here up to there. The third array here defines the shape. Time is y. No. The negative 3.9 is just the shape of the curve. Rather than being linear, think it's a curve. That's all that this one is doing. The y is the amount of time. Yeah. The delay of time, because you see where we're going to plug it in. Yeah. Well, yeah. That's exactly what it means. So rather than going straight linearly, rather than being a straight line, we have some curve to it. You see that curve, right? So negative 3.9 is just saying, here, baby. That's the amount of curve applied to the parabola. So Bearcat, if I did this, if I go positive 3.9 and I plot this thing again, and we superimpose it right below. Do you see how these two segments are different? Okay, so this third array just relates to how is the line shaped. If it's 0, it's linear. If it's positive values, this is the shape of the parabola. If it's negative values, this is the shape of the parabola. And that just gets down to quadratic formulas. Back to like high school math, algebra 2 or something. We're not going to go into it. We're just defining the shape. So again, this is points in time. So 6.0, 6.0, 0.07, 0.07. We're going to take 35 seconds to go between those two values. 35 seconds to go from 6.0 to 0.07. We're going to do it shaped with a negative inversion on it. Okay, and then next, we're gonna go from 0.07 to 0.09 in 130 seconds. So what's 35 plus 130? 165. And we see roughly, here's 150. This is a little bit accurate, so it's probably around 165 that we hit 0.09. Oh, everyone okay with that part? 0.09. Then we're going to go to 2.0. So we see in 50 seconds. So we know we're at 165. 165 plus 50 is what? 215? Yeah. So we see we've got another value here after 200, probably at 215. So there's 50 seconds to go to 2.0 with a curve of 0.99, nearly a little bit of a curve. Same thing. We're now going to go back to 0.01 over 80 seconds. We've got a really extreme exponent on that. And so we see it hanging out for a long time before it just hits. Okay, so this is one envelope we've defined. The second envelope we've defined in line 46 goes from 1 to 2 to 5 in 110 seconds, 30 seconds, etc. So we go from 1 to 2 in 110 seconds, linearly, 0. We go from 2 to 5 in 30 seconds with an exponent of -5. We go from 5 to 2 in another 30 seconds with an exponent of 2.9. We go from 2 to 1 in 160 seconds. So a really long, slow curve. So we're just finding these long envelopes over time. And then finally, we have this last envelope, line 51, which is linen. So it's got an attack, sustain, release. We're saying take 2 seconds to go up, hang out for 500 seconds, take 20 seconds to go down. 2 seconds up to 1, hangs out for 500 seconds, 20 seconds back to 0. So 3 envelopes. What are we doing with those 3 envelopes? Well, say again, Charlie? Yeah, so we've got this set of variables that we defined up top in MX gain out. So let's look at these. We've got in, audio in. It's actually sound in now. This is from a very old version of SuperCloud. But essentially, this brings in a microphone on channel 1 and applies some gain to it. We then multiply it by a really low frequency oscillator. And what you're going to hear is it essentially creates this like wobbling effect. Okay. And that is for the frequency. And then we're defining phase with another set of parameters. So we've got 2 oscillators going kind of in and out of each other. This is bad looking code. So here, let's just be a little bit more. This was written by a true composer, for better or worse. His name is John Drumheller. Huh? He's a Boulder, Colorado guy. He grew up in Bozeman. So we're defining an audio input. We're taking that input and we're multiplying it by a sine oscillator to give it some like oscillations. The frequency of this envelope, which gives us our frequency of the oscillator, is defined by this envelope R. So we have a frequency of 1252151 over the course of 500 and some odd seconds. Does that make sense so far here in line 55? Kind of. And then in line 59, we take the same signal and we multiply it by an envelope generator defined by X. So essentially, we're just turning on the microphone input in 2 seconds. It stays on for 500 seconds. Then we turn off the microphone input in 20 seconds. Everyone okay with that so far? Cool. Now we're creating an out signal. We're limiting it. So again, a limiter is just an audio processing thing we can talk about later. I'm hoping we still get the comb delays today because they're fucking badass, as you're about to hear, and we'll talk about why. So we're passing in our input signal. And then we've got this factor called delay time. And that's essentially how much delay is there in this comb delay filter. And a delay just takes a signal, delays it for some amount of time. In a comb delay, there's a feedback ratio, so it'll delay it multiple times as it slowly approaches zero on its decay value. We have 20 seconds for a 60 decibel decay, which we'll talk about a little bit more. And then we're doing the same thing where we're multiplying the amplitude of this unit generator by our amplitude defining envelope. Is that okay, Bearcat? Okay. Cool. Well, then let's listen to it and we'll see. We'll talk about it at the end. It's 9 minutes long. I want to listen to the entirety of it. We'll open it in. Yeah, we're going to. I just wanted to also be able to look at the waveform if possible. So we'll push, nope, we'll push the waveform right there. We don't need to see all the waveform, just the top of it. So we'll do this. And I'll work on moving through the score. And we'll start at the beginning, and I'll see you all in 9 minutes. I'll set the right output device. Zoom audio device. Okay, we'll start over. And just really quick to go over this score one more time. So this is for viola and supercollider. It's processed viola input. And so this top line is these are the timings for the viola player to then play their parts against supercollider. The second line is just the viola part. What we don't see in the score is the resulting or emergent composition. That's not represented visually, just as an FYI. Sorry, I'm actually going to do one more thing I realized. We're going to switch these. Of a performance of it. Yeah. No, it wouldn't, we can talk about the code in relationship to this in a moment. What I wanted to do, I realized though, is also show you. So down here, is the timestamp, yeah. Right, so that'll at least give us a sense of where we're at in relationship to this score. Okay, one more try. What in the hey, nothing here. Okay, play. Is this punk? Whatever. I stopped it. That's just applause. Mhm. I don't know. I don't know. Well, I think the recording would have been done with, I don't think the viola was going into Super Collider with, I think, a DI. I think the recording did not take advantage of the DI and just had a pair of boom mics based on what it didn't record. Yes, it presumably the recording was purely speakers, viola, two mics, and capturing it as it existed in the space. Probably in at CU Boulder. Huh? In the gruesome auditorium. Supervisor just runs, yeah. So you hit go and Supervisor just runs and it does this thing and you follow along the timing of Supervisor. The thing that's interesting about this is obviously a 20-year-old composition, which considering Superfighter is only like 25 years old, is pretty significant. It's using a very simple process. It's essentially using a comb delay for everything. You hit go, you see the code here, you hit go and it just goes.
Yeah, but is it static, static decline, or is it change?
Changes over time. That's the use of envelopes. So we see delay time on this delay changing as a result of this envelope. That's why we went over this envelope so quick. This envelope, you know the point where it had that? It's a good part. It truly is. Say again. This is just an amplitude envelope on the input, on the audio input. This is defining delay time. So when we hear the jump off point, so Dead Horse Point is either Arches or Zion in New Mexico. Apparently there was a bunch of wild horses that got chased to this point, and rather than be captured and broken, they chose to jump off the point into the valley below. So what he's trying to do essentially is create this sense of, at 4:55, this sense of franticness as they would jump to their deaths, right? So we're using a comb delay. A delay can actually affect pitch. When we take audio and we stretch it out, the pitch goes down. We can do that with a delay. Yeah, that's the analogy. And we see that happening. So that's what's going on right here. We've got this delay time going from 2 seconds to 0.1 seconds. Oh, excuse me. 2 seconds, 0.1 seconds. And then when we start going from 0.1 to 6, that's where we get the stretching. As we go and we stretch time out. The main point of this example right now, and then I want to talk more about the actual algorithm, but is to show that we can use envelopes for anything. Here we've got an amplitude envelope. It's defining the amplitude of a sound input. Here we have an envelope that's defining delay time of a delay. Essentially, it's like a delay pedal. It's just rather than reaching down and twisting it with your hands, it's programmed out over time. And so, yeah, you can get, and so this is one of my favorite things that I do for my improv stuff is really based on this. It uses a bunch of comb delays in series, and you can do some crazy pitch-based effects with delays. It's this unit generator right here, comb L. delay time.
Daytime.
Yeah.
Oh, because if you're stretching it out.
If you're not preserving pitch,
Yeah.
then it stretches the audio out and actually repitches it. Same thing
If it's
causes
negative delay time,
if it re- if it goes from long to short rather not negative.
yeah, but I mean.
It'll go
depending
higher.
on
Yeah.
how if you set the delay time.
Yeah. And then the oscillation, that wah, 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 that's this second envelope. That's that oscillation you hear. Wah, 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 wah. And it's, again, phase, so there's a left and right channel. And we are quarter oscillation off from left and right channel. It gives us that stereo sense. But we're just multiplying that by the sun. We're using a sine oscillator to multiply the audio input to get that wah effect.
I don't know.
I will put it up on Moodle. I'll put it up on Moodle. Yeah, I will. The code, unfortunately, like as you saw, the code is not updated for current versions of SuperCollider. But if you just grab this and replace this with sound in, let's see, where that go with that. Send me an email because I'm gonna forget this, but I will upload this on this weekend or Monday. Okay. Yeah. Here. And modern would be 0 because we're 0 based. It used to be audio in, and audio in was a shortcut to say that your one input would correspond to input 0, which caused more confusion than it was worth. So that's where there's a couple weird things. But this is a very simple, this is 70 lines of code. Really, it's really 35 lines of code for a 9-minute composition. That's the interesting thing. Envelopes don't have to be just amplitude gain. They are containers for any parameter. Envelopes are just signals over time that we can assign to any parameter. I know that makes you even more frustrated because the little bit of grasping you're doing then just vanishes into thin air. But the whole idea is that envelopes, and so envelopes can be used for composition over time, whether that's for a music sense or whether that's for a sound design sense. Just like tasks and other scheduling things, envelopes can be used to create complex evolvement and dynamicism over time. Fuck, where are we even at? Is anyone confused or understand what's going on? Cool. Okay, we're gonna quit today at 12:40, so we're only gonna take a 5-minute break. We're gonna come back and we're gonna at least look at sound input and how to record. Great. Yeah, this is a really, so this is the person who I originally learned Superfighter from.
Really.
Yeah. That's why I was such a clusterfuck for such a long time, because I learned it from a composer who was even worse at teaching it than I am.
Like I said, I've been just trying to pick up some things on a lot of people are using it really well. So a little bit outside of that, but, I really like this example of like, kind of just putting it-
Yeah,
this is so-
this work. Oh, fuck.
He's still working on it.
Yeah, he's still professor of composition down there. John Drumheller. Six. You're gonna get some horrible feedback there. Yeah, we are.
You gonna get some horrible feedback here? Yeah, we are. Yeah, we are.
Not remember these.
No, thank God. Do not. Okay. Good time. So you could change the wait time. The other thing you can do is system clock. Tempo. Tempo clock. So Sam, we could change the wait times and make those shorter. You can also change system clock. to be relatively fast. So just really quick, finish up one thing. I realized we never talked about the fact that you can just do tasks kind of procedurally. So you could write out inside of our set of functions. I can say, do something, wait 2 seconds. Do something else, wait a second. Do something, wait 0.5 seconds, etc. It's creating new synths actually. So in this example, we're saying create a task and then play that task. Play a sim, wait 2 seconds. Post this line dir, play a sim, wait 1 second for relative to tempo. Play a sim, wait half a second relative to tempo clock. Play a sim, wait 2 seconds. Play 3 sims at once, wait 2 seconds. If we wanted that to repeat, we could then go further and go int dot do. The piece that's given us as random is the carrier frequency. So if we just set this all to 1, then they'll sound exactly the same. What was your question? So it's going to repeat everything in here over and over again. We can speed it up by changing the tempo clock. It's unsatisfying right now because it's not a grouping of any sort of actual measure. Say again, Sam. You can do a lot with this. So you can be procedural. You could write out little patterns that would play over and over again. And just like synths, we can actually have, so we did away here. Um, we can play it together. We could actually also come in here to task. Quantization, so we can pass it a quant. We do it like this. But the cool thing about reset is we can just keep starting it over. Huh? I don't know what it's in. I need to add it out. Yeah, so you could actually have tasks launch other tasks. So we could have another task. So let's make this actually so it's 4 forward, make our lives easier. 1, 2, 3, 4, 1, 2, 1. 3, 4, 1. Okay. So now we can play both of those. We'll play this one. All right, so we can do that. If we have one playing, we can start it over. 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 And as Sam pointed out, we can say task 1 dot play. What was it? Do reset. Yeah, so do reset. So we'll always start it over. True. And then we'll wait 2 dot wait. We'll say 2 dot play to reset. True. And we have 2 dot wait. Task 1 dot reset. Task 2 dot reset. 4 dot wait. Task 1 dot stop. Four dot wait. 1 dot play. 8 dot wait. Say that again, Sam. This here is the number of seconds we're going to wait between things. So we'll launch this, we'll wait 2 beats actually. But in this case, they're seconds. And then we'll execute our next thing. So the other thing I like to do when I'm going this way is be really explicit. Step 1 post line. Step 2. Step 3. Step 4. Uh, we got these random doors in there. So they're overlapping with each other when they're starting and stopping. And we could even be, let's just be real cool here to make sure that we're always start of 2. So we can see when it starts. Start of 1. This is where post lines start to come in handy. You're giving yourself information to essentially debug your code to have some sense of either what's going on if you lost, or to help you make sure that it's doing what you think it's supposed to be doing. So we could see in step 1, we started 1. In step 2, we started 2. In step 3, we reset 1 and 2, so they both started. In step 4, we just stopped the task, so nothing happened in the task. In step 5, we started 1 and 2, because of where it was at, reset itself and started over again, and then they both stopped. 8 beats later. And you can go as complex as you want with tasks. You can go tasks inside of tasks and inside of tasks. But this can be a really nice way to start building up procedurally, in which case we're kind of doing it from a brute force method, a composition or a piece of some sort. Tell me that again. So let me just make, I think I know what you're saying, but I just want to say it back to make sure. So what's happening here is we're storing a task in the environment variable that we've labeled task 2. And we know it's an environment variable because it's appended with that tilde, so it turns pink. This could be dir. And then I would have to actually write dir.play. It's the tilde that makes it an environment variable. So the class task is what makes it a task. We've assigned this whole thing from here. So notice again, Superclass does this nice thing where it highlights matching brackets. So we see our bracket here to line 80. So we're taking the entirety of this block and we're assigning it to the environment variable task2 as a reference. And then we can later start it, stop it, reset it, etc. as we move forward. Yeah, it's just because in my head, it made sense to call it task2. If it made more sense to call it something else, we call it something else. We can think of them as equivalent to global variables, but they are called environment variables because there are no global variables in. It is an environment variable because you can create separate environments within SuperCollider. Whole, great. Whole, do I have that here? Whole. Holds a unit generator or a signal at a specified rate and reports back or posts its value to the post window. So if I open up help on poll, I know I've applied it to a unit generator. It tells me polls the output of this UGen every interval second and posts the result. In this case, it's every 10, it's a frequency of 10. If I've got poll trig and label. So if I say trig 1, it's going to poll it once a second. If I say 100, it's going to pull it a whole bunch. And then the other thing that can be useful, we haven't used as label, and this can be line value. And that can be a string, or infuriatingly, it can be a key. So poll is a way of debugging data in a synth in real time so that we can see what is the value of that signal. No. No. That's essentially, poll is essentially saying what's stored in on shape. So we could do the same thing here where we could say on dot poll it's just then polling that whatever signal is stored in this variable on. This is where it gets confusing because SuperCollider is made up of these two things, the interpreter, which is where we use post line, tasks live in the interpreter, math lives in the interpreter, and then the server, which is where we do actual audio processing. When we compile a synth definition or a synth, it creates a synth graph, it sends it to the server, and tells the server how to do something with audio signals. To get information then about that, we have to actually do some extra steps to get information from the server back to the interpreter so that we can then look at that values. So that's what poll is doing, is sending values from the server back to the interpreter and posting them for us. Does that make sense? So poll and post line are great ways of debugging code. Cool. Understanding what's going on or tracking down problems. Yeah. Or you listen and you go, that doesn't sound like what I thought it's supposed to sound like. And then you try to figure out why that's happening. Can be one way. It's also a good way of just getting straight up data back so you can understand what's going on. Cool. Fuck, let's record some sound so you can do something for next week. Okay. God, my mind is blown. We're defining a sim theft. We're not going to care about what the fuck the sim theft does. It exists. It does a thing. We can listen to it. Makes bubbles. Great. There are a couple really easy ways of recording in SuperCollider. The first is you can tell SuperCollider to prepare for record. Notice now it tells me preparing recording on localhost. That's the server that's running. Ignore the localhost piece for the moment. We have said this, but I've never said this explicitly. Always, or by default, assign to the local host. So the character S, again, A through Z can be used as environment variables. The character S by default is assigned to the local host server. Notice it says local host. Say again. S is for serve. If I write this thing, you can write .dump as a method on pretty much anything in SuperCollider, and it'll try to give you some information. So I write s.dump. Tells me it's an instance of server. And then it gives me some information. It's localhost, as much as it can. What is the current latency set at? Anything else useful in here? We don't have a scope window open. We have an instance of recorder that we've already started. Okay. So we've said on the server, we want to prepare to record, and then we're going to record. And it tells me now it's recording, and it tells me where it's recording. I can tell it to pause record, and start record, and stop record. And I can free the sim. Now, if I go to my Finder, and I say go to folder, and I paste in this location, it takes me to SuperCollider recordings. Here, path, it told me where it was recorded. By default, I think, is this in? There's a way to set this, but I don't remember how to do it. I'll look at that in a moment. So by default, though, on Mac at least, it stores it in your user profile under music. It creates a new directory called SuperCollider Recordings and stores it there. So you see the day at 12:16. We could open it, look at it. And it's going to be in the number, it's going to be the number of channels recorded is the number of channels that the server currently is running with. So we were running with 2 channels, it's going to record 2 channels. This is RX, Isotopes RX is a noise removal software. They have an audio editor for noise removal that I really like as just a visualizer, as a quick and dirty visualizer. If you need noise removal or other ways of cleaning up audio, I cannot recommend Isotope RX enough. I know. They do a couple things good. They do mastering software good and noise removal good. And then their meter plugins are really the best too. Anyway, sorry for nerding out on that for a moment. No. They're cheaper than Waves. What were you saying? No, that's exactly. Have you looked at how ugly SuperCollider is? That's free. Okay. So we're able to record easily. That's how we can record, right? If we look at the record method, if I pull up help on it, we notice we've attached the server. That's what we want to see. So let's look at server record. And you're actually going to notice I just pulled the help example right here from the help file. So this is what it is. I would encourage you to actually read through this so you understand what's going on here. Prepare record allocates a necessary buffer for recording the server's output. we can actually specify a path or number of channels in prepare record. So I'm going to do the following for a moment. Let's create a new SIMPDEF. Just to be explicit. And, what the hell are we running on? Node 2. Whatever, we'll just let's reboot and see where we're at. Root server. We are doing built-in micro, perfect. So we're going to say SIMPDEF. Basic mic in argument is going to be mic in channel. We're going to set that to 0. Variable is going to be sig. And then we're also going to have out channel, which we're going to set to 0. We're going to say sig is equal to sound in.ar. Bus is going to be mic in channel. So I'm pulling in the channel number that I want. This is a mono channel. And then I'm going to say, we'll leave it mono. And it's going to be very simple. Then we're going to go out.ar. Bus is going to be out channel. And channels array is sig. Dot add. Now, just so we can be explicit, X is equal to simp. Come on, fingers. Basic, like in. What's going to happen here when I launch this? We're going to get some feedback. So we see I've turned down the main amplitude gain on the big knob. As I talk, the inputs are going and outputs are going to 0. Just what I called it. Placing 0 there, 0 there. 0 is the hardware input with a zero-based system. That makes sense for everybody? Cool. Yeah, so that's just grabbing the mic input and we're passing it straight to the output. That's my mic. And we're gonna play this. Now we're gonna go S dot prepare for record. And we're gonna pull up what are my arguments again. I'm gonna look at server. And it's gonna tell me path and number of channels. Path. This is a big long string. We'll just steal what I had before as a basic starting point for it. Oops, that next one of those on both. User, music, and desktop, test, from SC.AIFF. And number of channels, how many channels should we record? 2. Cool. So we'll do that. It's going to tell me what's my issue here. Text. Oh, it's because here number. I forgot number of channels. Cannot define one and not define the others. Oh, worse. And there's path not understood. That should be desktop. User. Music. Oh yeah, that's gonna make life unhappy. That's gonna make life unhappy. Oh, no, I think it should actually be users. Yeah. Let me just see here. Maybe I didn't do that. No, come on. What is it? Okay, I think so. Okay, needs to be in a string, not with double quotes, not single. That's my bad. Number of channels are two. Okay, and are we still recording? So I can see I've got my U-Gen. And now I'm gonna go S dot record. We'll start recording. Blah, blah, blah. S dot stop. Recording. Cool. I'm gonna stop my synth. Stopped over here. We'll go to open a new tab here. Go to desktop. Sort by date. Test from SC. And when we open it with RX, we'll start recording. Blah blah blah. S dot stop. Recording. Cool, right? Makes sense? So we could also then, if we wanted to, test from SC-2, we'll say number of channels 1, because we're only recording one channel right now, right? Or we're only sending out. Record. So now I'm only going to get a mono recording. We'll stop it. We'll stop everything. We'll open it back up. Come to desktop. Open this other one in RX. So now mono recording. Record. So now I'm only going to get a mono. Cool, right? Okay. Tell me. You don't. So it's just if you want to use prepare or record if you need sample accurate start, you want to specify your own path. You want to specify number of channels. If we just, so we can hear, if you just need quick and dirty recording, you can just use s.record. So if we do this, I'm recording now. Notice that what it did is it actually prepared the recording with the number of channels and path, and then started recording. So it has to do two processes in one. Most of you are not sample accurate recording. You can pretty much just jump straight to s.record. It's just if you want to do your own path. The other reason why it's advantageous to use SC's path as it is date stamped. So you will not forget to change the file name and accidentally overwrite something else. So with this, if I did prepare for record, then record, and then I hit prepare for record and record again, if I hadn't changed this file name, I'd overwrite it. And if that was something I was trying to keep, then I'm in trouble. So it actually can be nice just to use SC's basic one. And then as soon as you're done with that, you go over to that folder, you grab the recordings you want and label them something that makes more sense to you. Drum sample 1, etc., and move them to a place that makes sense. If you don't change the path and you call s.prepare record, it will override itself. So right now I'm overriding the record that I had in there before on test from FC. And we will see that test from FC is now recent as of 12/29, but we initially recorded it a few minutes ago. You can do one without overwriting. And if you want to overwrite, that's fine. I just want to make sure you're explicitly aware of what's happening. If you want a different set of record format, you can actually call the record format AIFF as default. For most of you, the default record format is going to be fine unless for some reason you really need WAV. Most DAWs are going to allow you to bring in AIFF and convert it to WAV though. Same thing, if you want to change the sample format, you can do so. You can see these are being recorded with a sample rate of income stats. Does it tell me here? No. Shoot, what do I want to look at here? Info. Advisor. Come on, you got this. Was it still recording? That app's not working anymore. So it's sample rate of 48. It's whatever the system sample rate is set to, essentially. Okay. Finally, you can also shortcut with the server menu down below. So if we're playing here, I can click on server and say start recording. It starts recording, and when I'm done, I just hit stop, and then we'll notice I haven't been recording. It starts recording, and when I'm done, yeah. Default is the number of channels that your server is booted with, so stereo. You have to tell it to boot in 4 channels. We will get to that. Did I see your hand up? Oh. All right. What's going on? Okay, cool. Any questions about recording internally with SuperCollector? What's the other way we'd want to record? Yeah. Yeah. Okay, let's say we want to record into an MPC or into a DAW using a brute force hardware-based approach. How do we do that? Well, you're thinking of inter application routing for the moment. MPC is a hardware-based unit that's separate. You'd take a fucking audio cable, you'd plug it in from the output to the input of the MPC. If you're using another DAW hardware thing, or if you're internally, you could go just grab a short cable, go from the output to the input, record the own output of your own input. Yeah, it'd just be like any other hardware-based recording system where you're taking the outputs of something and plugging it into some audio-based inputs. That's the brute force way, and if you're doing the MPC, that's what you're going to do. Yeah. For the rest of us, we might want to use something called inter-application audio routing, which creates a virtual interface, just like this big dump here, but it's just virtual in our computer. It allows us to send audio from one application to another application without having to go out and back in. So I'll admit I'm a jerk and I don't know the Windows side of things quite as well. But in theory, there's these 2 applications by the same company. One is Voicemeeter, the other is VB Audio. And Maya, you're going to probably check this out and let me know if I was a jerk or not. Send me a message if you want to get together and work on this. Who else in here is PC users? So you got to use Jack Audio. That'll be your own help. For the PC people, let me know if this doesn't work if you want to do this. But you also can just, again, record using SC and then bring the audio file into whatever DAW you want. Supposedly, this donationware-based thing should allow you to do inter-audio application routing. They also have this virtual audio cable that should looks like we'll do the same thing. You don't have to, for the, so next week we have a midterm issue. I wouldn't, one of the options is that you can create a fixed audio file, and you could do that by actually composing something in a DAW or some other environment where you just took sounds from SuperCollider and then arranged them, processed them further, etc. So for those of us who want to get sounds out of SuperCollider into another environment, this is why we may want to record. Cool. So for those of us on Mac, the current thing that seems to be working well is something called Existential's Black Hole. You have to put in your name and an email address and register with them. And then you get the option of downloading 2 16 or 64 channel virtual interface. I would actually, depending on what you're going to be doing in life, I would encourage you to download both the 2 and 16 channel version, but you might want to just download the 2 channel only. You can certainly download 64. I did. Yes. This is not going to hit the interface. This is going from application to application. So what, for those of you who might bounce out of SuperCollider and work outside of SuperCollider, what environment do you think you'll work in? Ableton, Reaper, Pro Tools, what? Logic, Go. Ableton. Are you going to stay in SuperCollider, go anywhere else? What do you think? Totally different thing. Great. Ableton, probably Ableton. Harder. Yeah, great. Well, this will be applicable. Sam and Danny, you guys might just stay in SC or cool. So this would apply if we were in Reaper or Pro Tools as well. But we'll assume we're in Ableton. So I've got an Ableton session here. So virtual channels. It's like you've got that hardware interface of yours with 16 channels or however many does it have? 8? 12? And it doesn't exist physically. Poof. It only exists in the computer. And so it takes audio from SuperCollider, and it can take up to 12 channels of audio from SuperCollider into up to 12 channels of input to Ableton. Yeah. So in this case, I'm going to use Black Hole 2 channel. Gives me 2 ins, 2 outs. I'm going to set it to be at 48 hertz on both input and output. Great. I'm going to come over to Ableton. I'm going to say I want my audio input to be Black Hole 2 channel and my audio output to be Big Knob so that people can ultimately hear what's going on. Cool. We're going to delete my 2 MIDI channels. And we see now I'm bringing in external on a stereo. And we'll leave monitor off for just a moment. Now over in SuperCollider, this is where things get kind of weird. Because now I need to tell SuperCollider where to send audio. SC by default will use your system audio interface choices. So if we look right now at my system, I'm going to open up system preferences. I'm going to go to sound, output, and right now output system is set to Zoom. Output system input is set to internal microphone. When I hit reboot on the SC, notice it tells me it grabbed built-in microphone for input and Zoom audio output device for output by default. If I change my, if I change my system's default output to be Black Hole 2, and I reboot now, Notice I'm now going to black hole 2. Reboot the server, reboots the server, and looks at the new interfaces that you've told it to.
And SuperColor follows the system. SuperColor doesn't have a call.
Okay, so if I want to be explicit, I have to use server options. I have 3 minutes. Okay. Server options allows us to do a whole bunch of things like specifying in devices and out devices. So use to set server options, execute the following. O is equal to s dot default or s dot options, excuse me. Now O dot out device is equal to, I'm gonna grab this string. S dot reboot. It reboots with black hole output device. Likewise, if I change my system output to still be pointing to Zoom, and now I reboot SE again, it's still going to do what I've told it to do, which is use the black hole 2 channel. Okay. Now record in DAW. So let's grab the bubble synth. And if we look at our meter, we notice sound is going on. So we're outputting sound right now to this inner application audio interface. So it's gone to an interface out the 2 channels out. And now I'm going to come over to live and we see we've got audio coming in. And if I say monitor in, we're now going through live. So I can record in any of the ways I normally would record in live. Or I could record over here, right? So, and likewise, I can feel the volume in live. So we're sending audio from one to another. Why would we want to send audio from SuperCollider directly to a DAW? What's the advantages there? Rather than recording samples out of SuperCollider. Bearcat first. We could do that by recording in SuperCollider though and bringing that file in, right? Like I could bring in one of the files I recorded here, just and drop it in. Well, maybe find one that's not corrupted and drop it in, right? And I could still use it then over here. So why else might I want to go directly from SuperCollider? So Cole had to say that next method. Sorry. Yeah, so you could do it in real time. So you could then say, I'm going to play something and I want to do something in SuperCollider in real time and record it down, just like you would in a studio. Other ideas? There's reasons, workflow reasons why you may want to. You need an inner application audio interface. So Jack, nope, unfortunately not. Jack will do that on all operating systems. Black Hole is an open or freeware based thing that'll do it on Mac. This VB should do it on PC. If you want to go to a DAW. If you don't worry about it. No, you can do a fixed piece, you can do a coded piece, you can do something you do in a DAW. So let's take, I've got 3 minutes while I pack up here. Let me just make sure S. Oh man, I did not get through the things I wanted to today. So that's okay. So What questions are there about what we're doing for next week? So you have your first larger piece due on Friday. I'm gonna bring the sub in here. We're gonna do full critiques, talk about these pieces. Yeah, that's a great. I think I put that up already, but we can. Yeah, I believe that's on the GitHub. Well, anyway, I will send that out again in an email, but essentially, you're left pretty much to your own devices. What do I want to see? I want to see a deeper engagement in Superfighter than the sketches, such that there's a little bit more of a fully fleshed out piece, whatever that means. Somehow it changes over time, conceptual. What more than you have in previous weeks?